It appears we have been blessed by the AI gods again. During the annual I/O conference, Google introduced a bunch of new AI models, including Gemini 2.5 Flash, very fast, very cost-efficient model that achieves very good results, as well as the new video generation model that is able to generate outstanding videos. But in today's episode, we are gonna talk about Gemma 3N, which is a model designed to run on device locally and is able to achieve results similar to Claude 3.5 Sonnet. We are going to talk about the architecture, how they achieved such good results, as well as how to run the model locally. So without further ado, let's get started. So the first thing we have to do is look at the benchmarks. When we look at the benchmarks, we see the claim that Google makes that this model is able to achieve results similar to Claude 3.5 Sonnet. We have here Chatbot Arena benchmark. That is a standard benchmark that measures how good AI models are. It is designed sort of like a chess match between AI models, where the users are asked to blindly judge which model is better, and based on the number of matches the model wins, the higher score it gets. We also see on the benchmark that it is better than GPT-4.1 Nano, which is the smaller version of OpenAI's new bunch of models, and results better than Llama for Maverick. We can also look at the number of parameters, right? Because it's not meant to be state-of-the-art model. It's meant to be small model that achieves good results, but the main selling point is that it is so small and optimized you can run it on your phone. And we have the model weighs 4 billion parameters, so it takes this amount of space in memory. But we can also see that it is compared to models such as Llama for Maverick that has 17 billion parameters. But the thing you have to remember here is that Llama for Maverick is a mixture of experts model, right? So it has in this variant 128 experts, and during inference the text is routed to one or several of the experts. But it doesn't mean that it only needs 17 billion parameters to be loaded to memory to run. It actually needs to load all of the experts in memory for inference. Of course, it is faster than the regular model of this size because the request only goes through one of the experts, but all of the experts have to be loaded to memory at once. So it doesn't actually reduce the amount of RAM that we need to, or VRAM that we need to run the model. So this is important because this is the main distinction between a mixture of experts and the approach they are presenting here. Because in Gemma 3N, these dynamic layers are actually loaded from disk during inference. So we actually need less memory than if it was a regular model with standard architecture. So this is an important thing to notice because it can be confusing because mixture of experts are calculated differently, standard models are calculated differently, and here this Gemma model is calculated differently. So what you have to remember is that mixture of experts, it improves the inference speed but doesn't improve the VRAM requirements. But here in Gemma 3N, we actually improve the requirements, not necessarily the inference speed. So it is meant to lower the requirements to run on your phone. And of course, let's talk about the elephant in the room. You are probably not going to get Claude 3.5 Sonnet level of performance, at least not on every task. Of course, for coding, this model is not that good, but you have to understand, like, Google has to compare to someone, and Sonnet 3.5 is currently like state of the art model that everybody likes to compare to. But for me, the thing that you are able to achieve at least results in the same category as 3.5 Sonnet is truly impressive, because this model is very, very small, several magnitudes of size small, and it only needs about 4 gigabytes of RAM to run on your device. So it's not meant to be, state-of-the-art model. Obviously, this is far-fetched, than that here I guess on the specific subset of tasks, it can be comparable to 3.5 Sonnet, but it's not like you can ditch Sonnet and now only run everything on your device. But it is still cool nonetheless that you are able to even compare to the state-of-the-art models that are very large, proprietary, and have an open model running on device that is in the same category. So they use the model is able to achieve a dynamic number of parameters. So depending on the requirements that you have, depending of how much resources you have, you're able to dynamically sort of generate different model sizes. And we are going to talk in a minute about how it works. But this is important to know that the main architectural advantage of this model is you can steer, you can choose, mix and match, as they say, number of parameters that you need to achieve optimal performance versus system requirements trade-off. And they release two models, 3NE4B, which is larger model using effective 4 billion parameters, and 3NE2B using effectively 2 billion parameters. But this is just the two that they pick. You're technically able to choose the one you want that are aligned on this curve, right? They choose 2 points on this curve, and those are the models that they released, but you could technically choose any kind of model that you'd like. So let's talk about how they are able to achieve this dynamic trade-off. So first thing that we need to notice here is that the model uses something that they call conditional parameter loading. So the model is multimodal. It can process vision, images, video, and it can also process audio. Currently, the model that they released is only able to process text, but this architecture technically allows us to process vision and audio as well. And here they decided that if the user doesn't want to use the vision capabilities or the audio capabilities of the model, those parameters don't have to be loaded, right? Because they don't weigh a lot compared to the whole architecture, but they still, especially the audio one, use some amount of space in the memory. So the idea is pretty simple and obvious actually when you think about it. They decided that if you're gonna only talk to the model through text and don't need any audio or vision capabilities, you don't need to load those models at all. So we're able to save quite an amount of space, but simply not loading those parameters. So this is the first major thing. And by the way, we are only here working based on the very brief blog post released by Google. There is no technical paper or anything like that. So we have those scraps that we have to, use to make those kind of explanations. But I think we can still learn a few things. So the second thing that they mention is called PLE caching. This means that embeddings per layer can be cached and they don't need to be in the memory at all. So here is what they say. With standard execution, over 5 billion parameters are loaded when executing the model. However, using parameter skipping and PLE caching techniques, this model can be operated with an effective memory load of just under 2 billion parameters. So they mean that they're able to achieve 5 billion level performance with only 2 billion parameters effectively, so meaning being loaded at once, because there are other parameters, but they are loaded dynamically. And this is per layer, right? So what they visualize here on this graphic, that several of those parameters are loaded dynamically, it happens in every layer. So here we see the view of only one single layer. But you have to remember that this happens in all of the layers of the model. There are probably a couple of dozens of those layers. The second thing they say is that this model, how the PLE actually works. So those are only those two text fragments that we have from the blog post. So we are sort of guessing here, but we can use that. The PLE data can be generated separately outside of the operating memory of the model, cached to fast storage, and then added to the model inference process as each layer. So we know that we have some portion of the data that is static, right? Because if it's cached, it has to be static because it can't depend on the input. So this data is then added to the model to improve the performance of the model. But how does it work? Well, we don't know exactly, but we can think conceptually about this like that. So in standard operations, the model input is multiplied by weights, and input is the text data that we have. We can speculate that the input can be divided into two parts: static input, XS, and dynamic input, XD. Static input, we can think about it as a sort of, general linguistic truths and statistics of language, something that is always true about the language, something that can be learned by just analyzing a large volume of data, and it gives us certain, distributions that are naturally happening in the language, and they don't depend on the input data. This is like sort of a bias when you think about it. And then we have the dynamic part of the input. So something that is true only during this request, something that the user wants, something that the user asks about. If we then transform this equation, we can see that we can write it as weights multiplied by XS plus weights multiplied by XD. And since both weights and XS don't change during inference, we can cache this and we can put it in the cache and then load this from disk only when it's needed in certain layer, right? Because what we described it happens in all the layers. And then of course we have this dynamic part that needs to be calculated each time because it changes during each request. It is more of a conceptual representation of what is happening than an actual math, but you can use that to sort of visualize how is it possible. And of course, the other innovation that happens here is that the fragment that is cached can be loaded from disk, right? So because of this, they need obviously fast SSD storage, but it is only portion of the data and it can be fastly loaded and unloaded from disk, and it saves us a lot of VRAM and RAM requirements because the whole model doesn't have to be all in memory at once. So because of this, the model is able to run on mobile devices. But another interesting technique that the model is using, it's MatFormer, which the model is based on. And MatFormer was released in the paper in 2024 called MatFormer Nested Transformer for Elastic Inference. And it is an architecture variation of transformer architecture that is based on Matryoshka embeddings. So here on the left side, you can see the MatFormer block, and it is similar to the transformer block. It uses regular standard attention, then it has addition and normalization, but then where we in standard architecture have fully connected layer, something interesting happens. So they use, instead of standard embeddings and standard weights representation, they used what is called Matryoshka representation. And it is of course conceptually derived from Matryoshka, this Russian doll where you have multiple dolls stacked in each other, and when you open the larger doll, there is smaller door, and you can do it again. And the same thing is true for the embeddings that are present in this architecture. You have standard embeddings of standard size called XL embeddings, but then you also have smaller embeddings stacked in the larger embeddings, and they outline 4 sizes of those embeddings, right? XL, L, M, and S. But of course, you can have many different sizes of those embeddings. The important thing is that those embeddings get smaller and smaller. And how it actually works. So during training, we have different sizes of those embeddings loaded in the model. And then when we process the input through the model, we have a sampling algorithm that randomly chooses the size of the representations. So you can choose L in one layer, you can choose XL in different layer, and you can choose all of those. All of those can be chosen, essentially, right? And because all of those can be chosen, the model has to learn all of the representations at once. And it is important because in standard dimensionality reduction techniques, like PCA, you are able to do some statistics to shrink the representations because you have some linear correlations between different rows of the matrices and stuff like that. But then you are not guaranteed that those representations will be as useful as they could be. But here, during the Matryoshka embeddings, the model natively learns to understand all of the embedding sizes. Because when you think about it, if we can randomly choose between all of those embedding sizes, the model has to optimize for all of them. Because if we choose the L size embeddings in the first layer, doesn't matter what size embeddings we choose in the next layer, all of those have to be prepared that the embedding can be smaller, right? So that we can choose L size embeddings. And the same thing goes from M, S, and XL size for all of those sizes of the embeddings. So because the model is not guaranteed that it will get the best, the largest embeddings, it has to optimize for all of those embedding sizes. You can see that because this is true, the model needs to learn how to handle those sizes. Because as you know, in general, in AI, in machine learning, we don't solve the problem for the model, but we, in general, construct an environment and give a model a function to solve. And if the model is able to solve the function, we want the result to be useful. But it's up to the model how to solve this problem. We can't control that. So the same is true here. We can't control that the model will always choose the best representation for each size. But we can control that it will randomly get one representation of different sizes. And to optimize the loss function, in this case, next word prediction during the in the language model, the model needs to create accurate representations for all of the sizes because it doesn't know which size it's going to get. So in order to solve this problem, to minimize the loss function, the model needs to choose the best representations for all of the sizes. And this is actually very interesting technique, and you can read more about it in the Hugging Face article called Introduction to Matryoshka Embeddings, because those Matryoshka embeddings are quite recent, but not that recent, and they have been used for things like text representations, in sentence transformer library, also image encoding. This is very cool concept that is popular nowadays because we need to choose between different devices, right? We cannot always just optimize benchmarks and optimize the score to be the highest, don't caring for what the hardware user will be able to use. We need to optimize the models for different kind of hardware, for different environments that they will be working in. And Matryoshka embeddings are a very, very cool way to do that. So, as we said, during training, MatFormer doesn't train all of the granularities simultaneously in every step. It samples one of those granularities, so one of the sizes of the weights, and then computes loss and performs backpropagation only for the sample granularity. But because all of those are connected, all of those are optimized at once. So the important thing here to remember is that model has to optimize for all of the embedding sizes because it doesn't know which one it's going to get. This is the main principle of Matryoshka embeddings. So how it works during inference? During inference, you can actually do what is called mix and match. So you are able to choose, because all of those embedding sizes are designed to work simultaneously, you can choose the one you want that suits your hardware requirements. For one layer, you can choose XL size. For one layer, you can choose L size. For one layer, you can choose M size. And for next layer, you can choose L size again. It doesn't really matter because the model is, during training, optimized to work with any size of the embeddings. And this is actually what is able to generate this graph right here. So we can mix and match different embedding sizes, and for different size of the model, we are able to achieve different performance. And of course, the larger the amount of parameters, the better the accuracy of the model is. But the sort of genius thing here is that you can optimize it and choose it however you want. And this can also be seen in the graphics from the paper when they show here that mix and match for different kind of devices, you can choose different kind of sizes for the representations. And for the cloud, of course, you're going to use the largest representation and the most accurate version of the model. For local hardware, laptop, for example, you can choose mostly the largest size, and for some layers, smaller sizes. And for mobile phones and embedded devices, you will choose the smallest size. But you can freely play with those. And that's it when it comes to the architecture of the model. Because as I said, we only got a brief blog post, but Gemma 3N is mostly based on Gemma 3 architecture. And if you are interested in how Gemma 3 works, you can watch my previous video when we go into greater details about the training, the base architecture of the model and how it works. And most of the things will be also true for Gemma 3N. So if you want to dive deeper, I encourage you to watch this video. When it comes to deploying the model and using the model, as I said, of course, this model is designed to run on device, right? So our end application is going to be run this model on our mobile phones. Unfortunately, as far as I know, there is no way to run this on iPhone yet. But if you have an Android phone or you want to play with it and emulate Android phone with Android Studio, you can do that. All you have to do is download the Android Studio that you need to run this model on your laptop or your computer. Or if you have an Android phone, then you can skip this step and you can come straight to downloading AIH Gallery APK package. When you install this package, it will give you several functionalities of Google AIH, such as video analysis, text analysis, and so on. And in the AI chat models, then you can choose Gemma 3N to E2B for the smaller model and E4B for the larger model. When you choose the model, you will then have to log into Hugging Face because the model is open, but it is gated in the Google's Hugging Face profile. So you need to accept the terms and conditions on Hugging Face, and then you will be able to download the model. Once the download finished, you will be able to chat with the model and test it on your phone. If you don't want to if you don't have an Android phone and don't want to install Android Studio for the emulation, you can try the model on Google AI platform. You can choose between Gemma models, and then you can choose Gemma 3N and test the model before you jump to tinkering with it on your phone. Sort of very good way to test the model initially very quickly. You don't need to do anything, and then if you are satisfactory with the results for your specific use case, you can then deploy the model on your device. That's all for today's video. I hope you enjoyed it. As I said, the blog description that we are basing this on was very brief, but if you are interested in more technical details about Gemma 3N, you can come to my Gemma video and dive deeper into the model architecture. If you like the video, don't forget to give it a like and subscribe to our channel. Thank you.
Gemma 3 in the cut, running wild on my phone. Processing power, no cloud, all alone. On my laptop, see the queen of the zone. Real time moves, yeah, sitting on the throne. Gemma 3, yeah, she flexing in my head. Pocket Einstein, got the world at my command. No lag, no wait, every time she understands. Future in my palm, AI taking the stand. Tablet in my lap, she making it snap. Real time solutions, no time for the cap. Decoding data, peeling layers like a map. Gemma 3 the plug, always filling the gap.